Okay, let's keep talking RMS. This time we talk about RMS, and standard deviation, SD. RMS signal and the standard deviation signals are closely related. They have some interesting properties. Let's look the definition first. Let's look in the continuous domain. If we have a signal, let's say a voltage signal Vt, this is the t, the signal changes over time, like that. So the RMS signals, as we defined before, we'll take the Vt and the squared, then we take the mean, 0 to t, dt, integrate over between from 0 to t, then divide by t, that's the mean, then we take the square roots. So that's RMS signal. Then what's the definition for standard deviation V sub SD? Similar to that, we take the signal Vt and subtract the V bar with the mean, the signal, the average of this signal, and we squared and integrate over from 0 to t, and take the mean, and take the square roots. That's the standard deviation. Okay, so the V bar here is the mean of the signals, which is the integration from 0 to t Vt dt 1 over t. Okay, notice the difference. This means just integrate over Vt, RMS and standard deviation, you have to square the signal. And by comparing these two formulas, what we can tell is if the V bar equals 0, if the average, the mean of the signal is 0, essentially this equation are and this formula are the same. So that means the RMS signal equals the standard deviation of that same signal when average of the signal over a certain time is 0. Okay. So this is a very important conclusion here, and because for any AC coupled signals, we know there's no DC bias. That means when you average that over a certain time, the average will be a 0. Most noise signal electronics you can approximate to mean equal to 0 signals over a certain time. So in all these cases, we can apply the standard deviation properties to the RMS signals. Okay, just for the completion, let's also look at this the RMS and standard deviation in discrete domain. Discrete domain is common. Is when we have a sampler, we have a signal. It's an AC signal like this, but we have a certain samples distributed equally along this line here. And each samples, we call that samples VI. Okay, what's the RMS in discrete domain? We have same idea with VI each samples, square the samples, take the sum when I equal to 1 to n samples, divide by n, so that's the mean, then take the square roots. Similar standard deviation discrete domain we have is the signal Vi, subtract the V, the mean of the signals, and take the square, and use a summation from I equal to 1 to n, divide by n samples, take the square roots. Okay. So the V, when you sample the signal use ADC for example, so the V it will be equals to all the samples. We just see we have n samples here. All the samples we sum them together. I from 1 to n divided by 1 over n. Okay. Basically, any noise signals, and if the AC coupled signals, this mean will be 0. Okay. Now let's, if once we know this, just remember this. Once we know this, we can explore some very interesting property of standard deviation and apply that to the RMS signal. Here's the random noise signals I generated with the Python code. What I assume is here is 100,000 random samples, and what we plot here is only a subsection of these samples. That just means only 1,000 samples in this plot. And here is a histogram, this 100,000 samples. Because random samples normally it will follow a Gaussian distribution, like a bell curve. We all know that. You know the shape of the bell curve and the distribution of the samples will have a close relationship with the standard deviation. What we see here is for one standard deviation, for example, plus minus one standard deviation. That's basically this line here. What that means is if the samples standard deviation is plus minus one standard deviation, then about 68.3% sample will fall in this band. Okay, if you look at in time domain, that basically this line here and here. That means the amplitude of the samples, 68.3% amplitude samples will be in this range. And most commonly we use is this plus minus 3 sigma lines. That's commonly called like 6 sigma standard. That's plus minus 3 sigma. That's this red line here, and this red line here. This 6 sigmas means 99.7% samples are falling in between plus minus 3 sigmas. Okay, and in this time domain signals, we can see plus minus 3 sigmas as this red line here. So sigma, that means about 99.7% samples, the value of 99.7% samples will fall in this range, okay? And with 1,000 samples here, statistically, you can see only 1, 2, 3 samples go beyond this line. And in electronics, we commonly use this plus minus 3.3 sigma lines. That is a little bit further than 3 sigma line, this black curve in this histogram. What that means is if your samples fall in this range, it's about 99.9% samples will be in this band. Only 0.1% samples can go out beyond this band. Okay, let's clean up here and look this 1,000 samples example here. And the 3.3 sigma is this black line. And if we know these black lines, we can see it's pretty much a good representation of the peak-to-peak value of this noise signal, because only one samples are above or out this band. Okay, so now since standard deviation is RMS value when the average is 0, here we have average equal to 0 for noise signals. Now we can use we can relate the RMS value, to the peak-to-peak value with peak-to-peak values with the standard deviation. Okay, and that means if you know the RMS value of signal with RMS equal 1 volts, we know the peak-to-peak value roughly is about 6.6 times VRMS. Okay, it's 6.6 volts peak to peak. And other way around, if you know the peak-to-peak values, then you can also calculate a VRMS. That's basically equal to V peak to peak divided by 6.6. Okay, this is very useful when you try to analyze random noise signals or do some quick calculations. Let's look at a real-life example. Here, I'm looking at a very precision op-amp from LTC Analog Devices, LTC 2063. and you can see this voltage noise or this op amp here. This op amp is voltage noise, and this is between the DC and the 10 hertz. It's very important. It's low frequency noise. It's basically in a 1/2 noise band. And this is a time domain. We can assume this noise random distribution kind of follows a Gaussian distribution, and we can use the same rules. And here we can see it's 1 volts per division, and the noise, the peak to peak value of this noise roughly is 1, 2, 3, 4, 5. So it's 5 volts peak to peak values. And then what is RMS value? And from that rules, we can estimate RMS value of these signals. The RMS or some line around there will be the 5 microvolts peak to peak value divided by 6.6. That's RMS values. Okay, that's basically a very practical examples. When you see a noise signal like this, you can just estimate the RMS value. And most of the times, if it's a sampled signals, and then you can easily calculate the standard deviation with that samples. So if you know the standard deviation of the samples, and you can quickly multiply the standard deviation by 6.6, then you can estimate the V peak to peak values. Okay, these are just some quick tips here. Hopefully this can help you.